Morning, everyone. Welcome to the Maths&Stats webinar. Our first speaker today will be Cho from semigroups. He will talk about the inverse semigroup.
Thank you, everyone, and thank you, everyone, for coming. And thank you, everyone, for organizing this. And this is actually my first talk in Australia. So, thank you. And I'm giving a photo of my own talk experiences have been somewhat okay, sometimes bad. And unfortunately, I haven't tried this, so we'll see how it goes.
How was it for the audience?
I don't know. I don't know. That's fun. Anyway, so today I'll talk about inverse semigroups. So to do so, this is pure math talk. I'll start with definition. So I call S with a binary operation multiplication inverse semigroup. If, well, first of all, it is a semigroup, meaning that the multiplication is associative, and we have another condition. So for each S in S, there is this unique T in S, such that STS is equal to S and TST is equal to T. And we usually denote by T as S inverse. And yes, this is the inverse condition. Sometimes people call it von Neumann inverse. I've heard other names for it, but this is the definition. And what are the examples of inverse semigroups? Examples: any group is an inverse semigroup because every element has the inverse, and then that inverse does satisfy this condition. And another classic example is let X be a set, and let IX be a set of all partial bijections from X to X. So what do I mean by partial bijection? So if I have some set X and set X, there's some function, but the function does not need to be defined everywhere. It can be defined only in a subset of X, and then this is one. So yes, this is an example of partial bijection. And how do we compose them? So if they have, if another method is like this, and you compose exactly where they overlap. So here they overlap here, and this circle split here is the result. In this case, we actually allow some situation like this, where they don't overlap in the middle at all. In that case, we just have an empty blank. That's kind of a zero element in this semigroup, in this inverse semigroup. And this inverse semigroup is quite important in the sense that they model inverse semigroups. So there's something called Wagner Preston theorem. So in the group word, symmetry, groups of symmetries on some set X model all groups. So every group embeds in some symmetric group. This is kind of analog of Cayley's theorem here. So every inverse semigroup embeds into some IX or some X. So I learned this from Howson's famous book on inverse semigroups, that inverse semigroups capture partial symmetries as well, like inverse semigroups capture local and global symmetries. what do I mean by that? It's a very nice example, and I always give this example to attract on people. So we've got Sierpinski triangle and normal triangle. Sierpinski triangle, how to get them? You can search it on Google, which probably have a better picture than I draw. So there's this triangle, and imagine this was black colored, but I just removed this middle bit. So this is white. It's removed. And then you do that the same process to these three triangles. And then again. And then again. And then you will end up with a third. So here, there are lots of partial symmetries. So this whole picture will look exactly the same as this picture up here, but just scaled down. And this is well scaled down, but the same picture, same picture. So lots of partial symmetries going on. But if we just think of group of symmetries, then they have the same group of symmetries, S3, S3. So this don't capture these partial symmetries going on around here. To do so, we need inverse semigroups, and we need to think about these partial bijections. So that was my selling point for inverse semigroups. Good.
Do we know what the exact inverse semigroup of partial symmetries is?
Don't know. So I think for contour set, middle set contour set, I think the group of partial symmetries is polycyclic monite for two generators, but this one probably somewhat similar, but one needs to check. Good. So we've seen one definition for inverse semigroups. There's an equivalent definition. So S is an inverse semigroup. If S is a regular semigroup. What do I mean by that? So it's a semigroup such that for every S in S, there exists some T in T such that T in S such that STS is equal to S. So it needs not be unique. But to make it unique, we need to make all of its idempotents commute. The element here becomes unique, and then it's straight to all of these. And from this, we can also see some equational definition. So an algebra, some set with some operations. So this is binary, this is unary algebra, unary operations satisfying the following equational laws. So x, y, z is equal to x, y, z. And x inverse of inverse is equal to x. And x, y inverse is equal to y inverse x inverse. So up to here, it makes this algebra as a semigroup with English. But we need something more. So we have some regular element, and then we need idempotents to commute. So in the sense of universal algebra, this gives me that inverse semigroups form a variety of algebra. Good thing is that universal algebra gives us then three inverse semigroups exist. Now I can talk about three inverse semigroups after in almost 13 minutes. So I said it exists, but what is it? So there are a few descriptions, but I'll give the simplest description, but probably the useless description. So the first would be via quotient semigroups. So we have subset X, and we have X inverse. And we have three semigroup on X union X inverse, and then we need to quotient it by something. So we have some congruence rho on X union X inverse plus generated by the following. So for every word over X union X inverse, I make U is equal to U inverse. And then I make idempotent distributed. Every word. Then if I quotient this free semigroup on X union X inverse by this congruence, then this is the free inverse semigroup on subset X. And by the way, free inverse semigroup on subset X, I will always do it. And why does it not help anything? I think this kind of goes back to our discussion on free regular star semigroups that we've been doing with James Nick and T.S. that there are too many plural words. So for example, like inverse X, y inverse X. This is actually equal to, but how can you tell? If the words gets long and long and long, how can you tell that they are in my free inverse semigroup? So we need to come up with some normal form. And there are a few normal forms, but what I'll try to explain today is something called Munn trees. So Munn tree is for each element. Let's say for each element is W rho, where rho is the congruence. For each element in Fix X, I associate with some birooted and directed edge labeled tree called Munn tree. And then this is unique to this element. So how do I obtain? And there needs to be terminal, initial and terminal vertices. So how do I obtain? So given some word, W over X union X inverse, go to the Cayley graph of free group on X. And you read W from the identity of free group X in the Cayley graph. And you keep track of which vertices, which edges you visited. And take all visited vertices and edges. And get a subtree, a finite subtree, which I denote by MT of W for Munn tree. But we need to specify some initial and terminal vertices. So initial vertex will be the identity of free group on X, and terminal vertex will be where you stop reading. Where you stop reading, in fact, is the freely reduced word of W. So W inside free group on X. And we obtain this whole triple. So the initial vertex and then the terminal vertex and this underlying subtree. This is how we obtain a Munn tree, and I think this is best An example. So I will take I set x to be x and y. And what is your favorite word? Don't give me anything too long. X squared. Sorry, x squared y. X squared y. Good. Then let's go to the key graph on free group from two generators. Identity, and this is x. So how do I obtain a Munn tree? Or x and y? I just read. So I take this edge, I take this vertex, this edge, and this edge. And then I obtain and then this is the initial vertex, and this is my Munn tree, and this is representing this word inside my three inverse semigroup. And I'll briefly tell how to, I need to tell how to multiply these two normal forms. How do I multiply? So let's say I've got Munn trees like this. So the process is basically, I'm gonna overlap these two Munn trees together. But where do I overlap? I'm gonna overlap at this. So I identify the terminal vertex limits with the initial vertex thing, then I overlap. So overlap at this. And I need to clean up because there will be some overlapped edges and vertices. So clean up, I identify every overlapped edge and vertex. Then you have some underlying subtree, directed tree. And then what is my initial vertex? Initial vertex will be the initial of the first Munn tree, and then the terminal vertex will be the terminal of the second Munn tree. And that's how you multiply things. Any step? So let's say we've got this first Munn tree, and any word? Anyone?
X inverse y.
X inverse.
X inverse y.
X inverse y. Okay, let's do that. So x inverse y, the Munn tree will look like x and x inverse y. So I have x here, and x go back here, and then so I'm gonna overlap this Munn tree and this and this. So let's overlap. If I overlap, then I'll write the dotted edge. X, y, and then like this. And in fact, in this case, there is no overlapped edges or vertices. So you can just do this, and then just erase this. And this is the initial vertex, and then this is the terminal. And we have Munn tree for this multiplication. Good.
Can you give another example with some okay with you?
Should we start from this and then overlap this?
You can just add something like y inverse y in the middle of your second word, and then you get some overlap. In middle.
Yeah. And let's overlap. Oh, no, then this is not symmetry. Okay, what is this symmetry? So I go x inverse x, x inverse x, y inverse y, and x inverse y. So that will be x, y, this. And let's do that. So I overlap this on top of this and here. So I have y here. This is x. This is x. This is y. So this is overlapped. So I'm going to identify that. So I'm going to clean up. Remove this because I already have that. And nothing is overlapped, so I can just make this line and remove that. Oh, remove that. This is
This is the product of these two.
yes. Product of these two.
So what happened to that y? You didn't miss it.
Because we identified, because we already had. So here there was y, but we already have this y in the first tree, so we don't need to add any more. Any overlap we identify.
Wow. I mean, if you have y times y is y squared.
Yeah.
But with your notation, you get just one.
Here I just called it y, but in fact, because I started from here, I went y inverse squared and then y. So because the result needs to be some kind of a subtree in the Cayley graph of free group on two generators, and then in the Cayley graph of free on two generators, there is no overlap. This is just a tree. There is no like x like this. There is only one. So if this happens, like if when I overlapped, basically this happened. There are two edges with the same label from the same initial from the same source vertex to the end vertex with the same label 1. Then in that case I overlap. So in i.e. I fold. Yeah. You identify.
So the lack of multiplicity here is encoding the fact that x inverse x equals x.
Yes. Yeah. So I don't go x and x inverse and then I go to x and then x inverse. I don't add x, I just use the same edge. I identify. Any more questions?
So is it that when you do x, y, and then multiply by this word, the y inverse y, this is commuting back to cancel with the y?
Yeah, so x, y, and then if I think of y inverse y, and I go back, and then use the same edge to go up. Because there is already an edge. So when you overlap, basically, if there is an edge already with the label that you want to use, then you don't add. You think of it as already identified.
What if you just get rid of the y in the middle of the second element? So if it's
Yeah.
Just get rid of y. Keep the y inverse in the middle.
So x inverse y inverse x inverse y.
Like this.
No.
Then let's draw it. So we have this. And we want to overlap this with x inverse, and you want to go y inverse. We start x inverse, y inverse, and then X inverse and Y. Yes. So same, I overlap here. Then I will have Y, X, and X, Y, and that's it. So here, these two will be overlapped, these two will be, because there's an overlap. So I can remove this. We can remove this. We can just move this straight. Good. For remarks on free inverse semigroup. Next. So in the group word, every subgroup of a free group is free, but not every inverse subsemigroup of Fix is free inverse. So one of the easiest example would be take idempotence. So the set of all idempotents of Fix, then it's not free inverse. And to see what are the idempotents are exactly the ones with the terminal and initial vertices the same. So it looks something like this. And they're never any subset of this or this itself is not free inverse. And there is an open question still. Let's say I am given some inverse semigroup inside Fix. Is it algorithmically decidable whether S is free inverse or not? So in the case of group, it's trivial, it's always free group. In the case of, if we think of free semigroup, then given any S inside free semigroup, then you can decide whether that is free or not. But this is still unknown. And there is a characterization whether given an inverse semigroup S inside Fix, to check whether this is free inverse or not. But it's not very clear whether that's going to be decided. And there are lots of open questions inside free inverse semigroups. And as you can see, the multiplication is not that trivial. And if we go to free inverse semigroup on two generators, that's already quite large, that's already quite wild. So my supervisor Nick was sitting over there, and I decided to look at the monogenic one. So the monogenic one, which I'll denote like this. So it's generated by a single element, and the typical one tree looks like this. So this is the finite subtree. So finite directed path with some initial vertex wherever you want, and then some terminal vertex wherever. Or you can go something like this. I'm gonna make some table. Can I use that one? It's okay. Then I'll use this one. let's compare free inverse semigroups on one generator, monogenic one, with free group counterpart, which is the integers, and then the free semigroup counterpart, which is the natural numbers. And this is abelian, and this is commutative. This is, for example, x inverse x is not equal to x. And then we actually know every subgroup inside Z, which is either 0 or just PZ, which is Z. Every subgroup is indeed finitely generated, and here as well. So every subsemigroup is finitely generated. And this one. So for example, if you take the set of all idempotents, which I wrote here, with 1 here, then that's not finitely generated. And Z is finitely presented not only as a group, but as a semigroup. Because Z is also a semigroup, I can talk about semigroup presentation as well. And in fact, every free group is finitely presented as a semigroup. So there will be some x, and I need to specify an identity element, and x inverse x. Then that will give you elements make. And natural numbers is trivially finitely presented as a semigroup. And this is not. So this was proved by Schein in 1975, that this was not finitely presented, and it implies that no free inverse semigroup is not finitely presented. And do I have until 15? There are 2 rules that I want to talk about, but I think I might end up just talking about just one. And every subgroup, or even every semigroup inside integers, is finitely presented as a semigroup. And this as well, every subsemigroup is finitely presented as a semigroup. And we can guess that this is not, but we can characterize this a bit further. That characterization is useful. And the second rule that I wanted to talk about was Howson property. You might have heard of it, but I don't have to define it. I can just say it like this. Let's say G and H are some subgroup inside Z, and in fact it can be subsemigroup. Then, and I suppose G and H are finitely generated, then G intersection H is also finitely generated. This is true for, if I take just subgroup, this is true for any free group. And that's the way, and that's proved by Howson, and that's by Howson. And here, S and T are some subsemigroups inside natural numbers, and then ST are finitely generated, and S and T is. And you can guess this is no, but there are some 2 different kinds of answers. So, yes, if both subsemigroups I take happen to be inverse subsemigroups, both are inverse. And no otherwise. So what I want to talk from now on are these two, but I think I'll end up picking up this one. So I would like to give some definitions on free per semigroup from single generator. So this is what we saw as a just typical element. And if I write typical elements like this, and let's say my initial vertex was here, terminal vertex was here, but this can go to the outside. Then how many edges are here? I just say A edges here. And how many edges from the initial vertex to the right end? So then I say P edges. And what's in the middle between initial and terminal vertices? I say absolute value P edges, absolute value P, because if the terminal vertex is on the right hand side of the initial vertex as in this picture, then I take column. If this is on the left hand side, then I take negative. If they coincide, then I'll take just 0. So every element inside HIS1 correspond to some Munn tree, but the Munn tree can be parameterized with 3 triplets, which I write minus A, P, B, with A and B are positive integers or 0. But because this I'm talking about semigroup, I just have to take, I have at least one option. And P can vary between minus A and B. And minus A P P is positive if B is positive, negative if B is negative, and idempotent if B is. And I say, I'll give just 2 more definitions. Let's take any subsemigroup inside free per semigroup on one generator. By the way, this semigroup, I don't need to take S to be an inverse semigroup. It can be just any semigroup. Because inside free inverse semigroup on one generator, or in fact, inside any inverse semigroup, you can take just a subsemigroup, or you can take inverse semigroup. But this time, I just take the some subsemigroup. And if P is wholly contained inside I'm looking. Sorry, I need one more definition here. So I write P to be all positives and N to be all negatives and E to be idempotent. So given S a subsemigroup inside a free inverse semigroup on one generator, if S is wholly contained, positives or negatives, positives or idempotents, or S is wholly contained in negatives and idempotents. So in other words, I see only positives or zeros, positives or idempotents, but no negatives here. I see negatives and idempotents, but no positives here. Then I say S is one-sided. If I see some positives and I see some negatives as well, then I say S is two-sided. So I said I'm going to fill in this, I'm going to talk about these 2 bits here. I will elaborate more on this first bit. So this was what I did with my supervisor. So we like to characterize what subsemigroups inside free inverse semigroup on one generator is finitely presented, or when is it finitely presented, when is it not finitely presented. And that has a very simple description here. Let's take some finitely generated subsemigroup inside free inverse semigroup in a single generator. Then S is finitely presented as a semigroup. If and only if S contains only finitely many items. That is if and only if when I see this generating set A is fully contained in positives or idempotents, or really as A is fully contained in negatives or idempotents. And that is if and only if S is one-sided. As in this case. Whenever there is S that is two-sided, it's never going to be finitely presented as a semigroup. But if S is one-sided and it happens to be finitely generated as N, then it's finitely presented as. Right. I think 5 minutes is too short for me to talk about this. So I think I have to stop now.
You can write an example here, so if you have an element, what do you write as minus A P?
So let's usually there's I have 2 edges here, and then 3 edges there, and then I have 2 edges between, and then the terminal vertex is on the right hand side of the initial vertex. So in that case, this corresponds to -2, 2, and 3. So 2 is there, and 3 is there, and then 2 in the middle.
And see, what's the actual element here? I mean, you have an X, everything generated by X and X in.
Yeah,
What's the actual element
Uh-huh.
that represents? What is it?
In terms of words?
Yeah.
Okay, so that will be x to the -2, and then I go back x to 2, and let's go all the way up here, so that will be x to the 3, and then all the way down here, -3, and then x to 2. So these 2 here are idempotents.
Elements are not unique.
In terms of words, it will not be unique. There will be lots of words represent this. But in terms of one tree, it is unique. And then because I got this triple from one tree, this triple will be unique. So for example, in terms of words, you can use these 2. This is an idempotent, this is an idempotent, we can read it. We see elements inside free inverse semigroup in one generator, but they represent the same entry. And they have the same. No, my calisthenic triple is coming from not completely different, but we need some other definition. My calisthenic triple comes from the unit and partially ordered set, right? And so you need semi-logicity inside partially ordered set, and you need some action from.
Say one many items.
Mhm.
This very much feels like it breaks because in your presentation, you either need to add relations for each item, but to be an item for to communicate, I guess, is that roughly the right idea?
What do you mean by break?
For you to not have a finite presentation.
So when you have infinitely many idempotents,
Yes.
then you don't have. Yes, that's very much the idea. So there are infinitely many idempotent, then you need all of them to commute. To do so, you need infinitely many ranges.
I'm guessing that's not easy to show them.
Yes, so what we did, we actually didn't come up with exact presentation because we had Schein's presentation for the whole inverse semigroup on one generator. And then we did some mapping onto it. And then we restrict that map to some inverse, some subsemigroup with infinitely many idempotents, and then that makes some